In this particular set of notes, we're going to talk about systems of linear equations. So in general, the term systems of equations means that we're actually going to have two functions at the same time, if you will. Now, we're going to see through the next couple lessons that there are multiple ways to solve systems of equations. We're going to start with the first method of solving systems of equations, and that's through graphing. Now, we're going to keep our lessons limited to linear equations, so we're going to be dealing with linear functions. Now, keep in mind that since we have two linear functions on a graph at the same time, the whole thing by itself is not a function. We're talking about two separate functions being used together, and we're going to see what that creates and how we find answers for that. And so you can basically see here we have a first example with equation 1 and equation 2, and both of these equations are written in standard form. Your system of equations could also be written in slope-intercept form, so long as there's two and you have an x and a y in both of them, or if you don't have an x and y in both of them, you're probably dealing with vertical or a horizontal line, so just keeping those special circumstances in your mind. So what we're trying to do when we're looking at solving a system of linear equations is to find the solution. Solution is just a special word for what is the answer. And in this case, remember, a solution is an ordered pair that makes the linear equation a true statement. And so that's basically what we're doing here, is trying to find an ordered pair that makes the linear equation a true statement. Now, the fact that we're dealing with two linear equations, the same ordered pair has to make both linear equations a true statement. And so basically what that looks like graphically is an intersection. So if we were to draw two lines and they were to cross, the point where they intersect would actually be the ordered pair that would create a true statement for both of them. So it's important that you understand what a solution is and what it looks like. There will be a few special circumstances in this particular set of notes that you need to be familiar with. So let's just take a quick example here and see if we can just identify a solution. And so example 1 says to check these two ordered pairs to see if they're solutions to the system of equations. And so the way we do that is simply to evaluate by plugging in the ordered pair into the equations. And if it creates two true statements, then we know it is a solution to the system. And so you can see for part A, we plug in the ordered pair 2, 2 to both equations, and we get a true statement in both cases. And so since that's the case, 2, 2 would be a solution or the point of intersection. Keep in mind, in this case, 2, 2 would be a point of intersection if we're looking at a graph. Now, it should seem fairly obvious to you at this point that there can be only one point of intersection between two lines. So if 2, 2 is a solution to the system of equations, and it is the point of intersection, then 0, -1 could not be. But you could still test it. And so if we look at part B, we took 0, -1 and we plugged it in, and you can see that it fits for one of them, which means that 0, -1 is a true statement for equation 1, which means that it is a point on that particular line. It is just not a point on both lines because it doesn't check for the second equation. And so just because it works for one doesn't mean it's a solution to the system. So let's keep that in mind as well. So go ahead and take the time right now to pause the video. Sample problem number 1, we're just simply asking you to check if those are solutions to the systems of equations. So go ahead and do that at this point. Okay, so I'm going to start with part A. I'm going to check these equations for the ordered pair 1, 4. So I'm going to plug in 1 for x, -3 times 4 equals -5. It's going to give me 1 minus 12. And that's going to give me -11, which clearly does not equal to -5. And so in this particular case, since that statement is false, that's a false statement, it's not a solution. Now notice I didn't even have to check the second equation, because if it's not a solution for one of the lines, it can't be a solution for both of the lines. So that's a good indication we can go ahead and stop. Alright, for part B, -5, 0, we'll go ahead and plug that into both parts. So that's -5 minus 3 times 0 equals negative 5, and of course that gives us negative 5 equals negative 5, so we're good so far. That's true, but just because it's true for one doesn't mean it's true for both, so we must test both of them. So we're going to take the second equation and plug in our values, and then that's going to give us 10 equals to 10, which is also true, and so we can say that this is a solution, and since it's a solution, that is the point where the two graphs would intersect. Okay, and that's just a quick introduction to systems of equations. In this example, we're going to take a look at how we would solve a systems of equations. Now, we're going to learn in lessons after this that there are multiple ways to solve a system of equations. The first and most popular way that you would know how to do this is through the graphing method. Since you've learned how to graph a line, you can simply graph two lines on the same graph and look for the common solution. So that common solution, or that common ordered pair that makes both statements true, will be the point where both graphs cross each other. So in this particular section, we're just going to focus on solving these systems of equations by finding the point of intersection between two graphs. Now, a couple situations that you'll have to deal with. If you look at example number 2, we've given you two equations. Both of them are in standard form. So you've got a choice here as to what you can do. You can either take that and convert it to slope-intercept form for both parts, and then graph both of them in slope-intercept form, or you can do the intercept method. So if you want to graph both of the intercepts, so you could say graph both of these points and end up graphing both of the lines that way. It's your choice, whichever way you feel is going to be easiest for you to graph the two lines. Now, what we're ultimately looking for here is this, that we get both lines graphed, and we're looking to identify that point where they intersect. And so you can see here in the solution, we've graphed both lines, and we've got this point 2, 1 is the point of intersection. And so 2, 1 is actually the ordered pair that makes both of the statements true, or both of the equations true. So since it's true for both of them, you know that it is the solution to the system of equations. Now, we do have one drawback with solving systems graphically, in that since it's in a visual format, if you're not very particular about where you plot your points and drawing your line with a straight edge, and you don't get a good clean intersection, you may not be able to tell the exact point if it's not going exactly through a grid line. And so you're going to need to pay particularly a close attention to the way you go about graphing these things. So let's go ahead and take a look at sample problem number 2. You have a system of equations here, and you have one choice. You have a couple choices here. You can either graph them using the intercept methods, or you can graph them by converting them to slope-intercept form. So go ahead and choose your method of graphing both the lines. Remember, graph both lines completely on this graph, and go ahead and pause the video now and do that for me. Since everything's even, I'm going to choose to actually just go ahead and convert this to slope-intercept form. I think that would be an easier method. And so I'm just going to go ahead and convert these, and then I'll get both of these lines set up and ready to go. I've converted both of these to slope-intercept form now, and I'm just going to simply graph both of these lines on the same graph. Now keep in mind, this is different than a piecewise function. On a piecewise function, we were graphing two parts of a line, but we had a range of values that we didn't want to use. That's not what we're doing here. We want to graph the entire line for both lines across the entire graph, and make sure you're not using a little bitty short line. Sometimes if you do that, you won't see the point of intersection. We want to graph them fully and wholly all the way across the whole graph. So I'm going to go ahead and graph that right now. Y equals x plus 4. Start at plus 4. Up 1 over 1. Up 1 over 1. Okay, and so you can see here I've graphed the equation y equals x plus 4. Okay, now I'm going to graph the second one, y equals negative x plus 2. Start at plus 2 from a y-intercept, and I'm going to go down 1, back 1, down 1, back 1, and now I'm going to graph this line. And now you can see that I've graphed the line y equals negative x plus 2. Okay, and so what we're looking for here is we have both of these lines graphed on the same coordinate plane, and we're looking for that point of intersection where they're going to cross. And so we can kind of see here, if we go back 1 and up 3, we can kind of see that that's their point of intersection. And so in this particular case, -1, 3 would be the solution to the system of equations. Now, if you had not taken your time and drawn a nice line with a straight edge and gotten a good clean line on both of those, you may have not seen it cross exactly at that grid point, which could cause a problem. So be sure to take special care with your line. Okay, so that is solving a systems of equations through graphing.